13.8 billion years ago, the universe was a furnace. In that primordial soup, the laws of physics were generating matter and antimatter in absolute equality. For every electron, an anti-electron. For every quark, an anti-quark. These twins were identical in mass but divergent in their charge, locked in a lethal embrace. Every time they met, they annihilated in a flash of pure gamma radiation. This struggle was a cosmic war where every birth was also a death sentence. The expected outcome of this perfect symmetry was total erasure. The universe should have remained a featureless void of light, eternally expanding and eternally empty. In a symmetric cosmos, stars never would have ignited. No planets could have coalesced. Instead, the darkness would have remained absolute. But the void failed. For reasons that science is still struggling to define, the symmetry broke. For every 10 billion particles of matter that met their end, one single particle survived. This tiny remnant, this microscopic survivor, is the reason the stars burn and why the ground beneath our feet exists. We are the children of that one survivor. This narrative is more than a lecture on the mechanics of subatomic decay. Beyond a simple lecture, this investigation represents a profound inquiry into the nature of existence. If the laws of physics were truly fair, the universe would be a dark, silent vacuum. Our very presence is a glaring anomaly, a lucky accident of cosmic bias that allowed substance to triumph over nothingness. We are the living proof that the universe is not as symmetric as we once believed. This asymmetry represents the most significant mirror break in the record of time. Today, deep beneath the border of France and Switzerland, the most expensive machine in the record of humans is searching for the source of that bias. At CERN, the Large Hadron Collider accelerates particles to nearly the speed of light before smashing them together. These collisions recreate the intense heat of the first 1/1,000,000th of a second after the beginning of time. Scientists are looking for a crack in the standard model of physics, the governing rules for all known particles. This theoretical framework has stood for decades, but the visible universe proves that the framework is incomplete. We are hunting for the mechanism that saved matter from total erasure. We have spent billions of dollars to build the most complex laboratory in existence. This facility represents a triumph of human cooperation. The laboratory also represents a profound admission that humanity remains ignorant of why the cosmos exists. Smashing particles together is a very expensive way to ask a question that the universe refuses to answer. Over the chapters ahead, we will descend through the layers of the subatomic world, following the 1928 prediction of Paul Dirac, who first realized that every particle of matter has a hidden mirror image shadow. The hunt for mirrors takes us into the alpha experiments, where researchers trap antimatter in magnetic cages to see if the reflection is perfect. These discoveries pave the way for the latest breakthroughs at the LHCb detector, where physicists finally decoded asymmetry in baryons, protons, and neutrons. These heavy particles are the building blocks of every atom in the cosmos. We must also decode the 3 requirements of Andrei Sakharov, the essential conditions that explain why the early universe did not simply vanish. The investigation traces the path from the first shocks of 1964 to the newest frontiers of 2025. The story reveals how quarks and rare particle decays known as penguins, loops in the subatomic world that allow one quark to transform into another, conspire with mirror worlds to forge the visible universe. Finally, the search leads to the hidden bias in the heart of the Large Hadron Collider. Why does substance exist rather than a void? This question represents the core of our journey. We are the descendants of a cosmic era. We are the remnants of a bias that the laws of physics seem to hide. The existence of every planet and every star is proof of a lucky break in the early universe. Understanding this break is the only way to understand our place in the vastness of time. Our presence is the result of a single particle out of 10 billion that refused to vanish. The investigation begins now. If this kind of deep exploration resonates with you, if you value understanding over easy answers, consider subscribing. And if you are able, donating helps us keep making these long-form investigations. Either way, thank you for being curious. The journey back to the beginning takes us to a state of existence that defies every intuition. 13.8 billion years ago, the universe was not a place. The cosmos was a furnace, a singular point of infinite density and temperature, expanding outward at a speed that defies human comprehension. In this initial moment, the temperature was 10 to the power of 27 Kelvin. At this scale, matter as we know the substance, solid, stable, and enduring, did not exist. No atoms floated in the void. No nuclei formed. Only a primal soup of fundamental particles existed, a plasma so hot that reality boiled in primordial heat in a state of chaotic flux. In this boiling chaos, the laws of physics enforced a strict, ironclad rule, the rule of symmetry. According to the standard model of particle physics, energy converts into mass in pairs. A mechanism cannot create a particle without creating an antiparticle. For every electron birthed from the energy field, a positron is born. For every quark, an antiquark appears. These twins are identical in mass. The particles are identical in spin. The pair differs only in charge. The entities are perfect mirror images of one another. Like reflections in a mirror, the twins are inextricably linked by the geometry of creation. The symmetry comes with a lethal price. Matter and antimatter are natural enemies. The two substances are the ultimate antagonistic forces. When a particle meets an antiparticle, a pair does not bounce off each other. The twins do not bond. The entities annihilate. The collision cancels the check of existence. In a flash of gamma radiation, the mass reverts instantly back to pure energy. E equals mc squared, played in reverse. Picture the early universe. The cosmos is a dense, hot, expanding arena. The space is filled with a cosmic war. Trillions upon trillions of particles pop into existence, only to instantly collide with mirror twins and vanish. Birth. Annihilation. Birth. Annihilation. A continuous, violent cycle of creation and destruction defined the first moments of reality. If the laws of physics were perfectly symmetric, this war should have ended in a stalemate. The matter should have destroyed the antimatter. The antimatter should have destroyed the matter. The results should have been zero. The universe should have cooled down into a vast, expanding sea of light. A cosmos filled with photons, but nothing else. No protons would exist to form hydrogen. Fusion could never light the stars. Carbon would never build life. Just a cold, dark, empty void, rippling with the fading heat of the Big Bang. This mathematical model represents the universe that the equations predict. A universe of perfect, sterile symmetry. But look at the reality. Look at the ground beneath the floor. Look at the hand in front of the face. The human body consists of matter. The earth is built of substance. The sun is made of matter. The Milky Way galaxy contains roughly 1.5 trillion solar masses of matter. Astronomers have looked deep into the cosmos, scanning the space between galaxy clusters, looking for the telltale gamma-ray signature of matter-antimatter annihilation boundaries. The search found nothing. The observable universe, spanning 93 billion light-years, appears to be made entirely of matter. The antimatter is missing. The discrepancy is the single greatest crime scene in the history of science. Somewhere in the first fraction of a second, the perfect symmetry broke. The stalemate was rigged. For every 10 billion particles of antimatter that died in the Great Annihilation, 10 billion particles of matter survived. Think about that ratio, 6 parts in 10 billion. Imagine flipping a coin 10 billion times. Probability suggests 5 billion heads and 5 billion tails. But imagine getting 5 billion heads and 5 billion and 6 tails. Tiny deviation, that statistical whisper, is the only reason humanity exists. We are the survivors of a cosmic purge. We are the result of a slight, unexplained bias in the laws of physics that favored substance over emptiness. The realization forces us to ask why the laws of physics possess such a hidden, vital bias. The mystery brings the investigation to the first major lead. To understand the missing antimatter, we first have to understand the nature of antimatter. To do that, the journey must travel back to 1928, to a desk in Cambridge University. There, a quiet, socially awkward physicist named Paul Dirac was about to rewrite reality. Paul Dirac was a man of silence. Colleagues at Cambridge joked that the vocabulary of the man consisted of yes, no, and I do not know. Imagine a man sitting in a Spartan office, surrounded by the smell of old paper and the scratching of a fountain pen. Dirac was not looking for a new type of matter. The physicist was trying to solve a theoretical headache. At the time, physics was broken into 2 warring camps. On one side stood quantum mechanics, the new rules for the very small. On the other stood special relativity, the rules of Albert Einstein for the very fast. No one had managed to make the 2 theories play nicely together. An electron moving near the speed of light broke the Schrödinger equation. The math was a mess. Dirac sat down to write a new equation, a relativistic wave equation for the electron. The physicist worked with 4x4 matrices, manipulating symbols on a page, guided by a sense of mathematical beauty. The work was not a simple calculation. Dirac was attempting to merge the world of the infinite and the world of the infinitesimal. The calculation required a new kind of algebra, a way to describe how an electron spins and moves through space-time without violating the speed of light. When Dirac finally derived the famous Dirac equation, the result was elegant. The math was concise. The formula perfectly described the spin and magnetic moment of the electron. The work was a triumph. But the equation had a dark side. The math predicted 4 solutions. 2 solutions corresponded to the electron we knew, a particle with negative charge and positive energy. But the other 2 solutions described a phenomenon that seemed impossible. The math described a particle with positive charge and negative energy. In 1928, this prediction was nonsense. A positive electron? The concept did not exist. Physicists tried to ignore the result. The community tried to dismiss the finding as a mathematical artifact, a glitch in the formalism, but Dirac refused to blink. The physicist looked at the equation and concluded that if the math is true, then the particle must be real. Dirac initially thought the particle might be the proton, but the mass was wrong. The math demanded a particle with the same mass as an electron, just with an opposite charge. Dirac postulated a sea of negative energy states. The physicist imagined that what we call empty space is actually filled with an infinite sea of these negative energy particles. To visualize the sea, imagine an infinite ocean where every possible position is filled by an invisible electron. You cannot see the ocean because the water is everywhere. This action leaves behind a hole in the ocean. That hole would behave like a particle with positive charge. Dirac called the entity an anti-electron. Think of this sea like a packed ballroom where every square inch of the floor is occupied by a dancer. To an observer from above, the room looks like a solid, unmoving block of people. You cannot see any individual movement because no space exists to move. But if one dancer suddenly leaps out of the room through a window, a single empty space appears on the floor. Now, the dancer next to the gap can move into the space. Then the next dancer moves into that new gap. To the observer, the whole appears to be traveling across the floor like a ghost. This moving absence of a person behaves exactly like a real person, just with an opposite direction. The insight was the genius of Dirac. The physicist realized that antimatter is not necessarily a different substance, but a hole in the fabric of reality. The idea was radical. Dirac was predicting a new form of matter based entirely on ink marks on paper. But the universe loves mathematics. The pieces did not fit the current model, but the math insisted the model was wrong. 4 years later, in 1932, an American physicist named Carl Anderson was studying cosmic rays at Caltech. These rays are high-energy particles from deep space, messengers from supernovae and distant galaxies that constantly bombard the atmosphere of the Earth. Anderson was using a cloud chamber, a sealed vessel filled with supersaturated alcohol vapor. Imagine the scene in a darkened lab. The air is thick with the scent of isopropyl alcohol. Inside the chamber, a fine mist hangs in the air, waiting for a visitor from space. When a charged particle zips through the chamber, the particle ionizes the air, leaving a trail of tiny droplets, a white streak in the mist. By putting a strong magnet next to the chamber, Anderson could make the particles curve. Negative particles curve left, positive particles curve right. The radius of the curve reveals the momentum. The density of the track reveals the mass. On August 2nd, 1932, Anderson captured a photograph that should not have existed. The image showed a particle track passing through a lead plate. The plate was 6 millimeters thick, about the thickness of a pencil. This lead barrier was critical. As a particle passes through the metal, particle loses energy and slows down. A slower particle curves more sharply in a magnetic field. By measuring the curvature before and after the plate, Anderson could determine exactly which way the particle was traveling. The curvature proved the particle was traveling upward, entering the metal plate from the bottom. The curvature also proved the particle was positively charged, but the track was too thin, too long, and too curved to be a proton. A proton is 1,800 times heavier than an electron and would have plowed through the mist like a freight train. This visitor was nimble. The particle had the mass of an electron. The track was the ghost of Dirac. Anderson named the particle the positron. The entity was the first antiparticle ever discovered. With this discovery, the symmetry of the universe was confirmed. Physicists realized that every particle in the Standard Model has a mirror twin. Antiprotons exist. Antineutrons exist. Antineutrinos exist. Nature can, in theory, build an entire anti-world. Anti-hydrogen atoms made of antiprotons and positrons, anti-water, anti-stars. But the discovery only deepened the mystery. If antimatter is real, and if the substance is created in pairs with matter, Then where is the rest of the antimatter? Why is the universe not filled with anti-stars? Why are we not being bombarded by anti-galaxies? The discovery of the positron proved that the machinery for symmetry exists, but the universe we reside in is undeniably asymmetric. Science needed a mechanism. We needed a way to break the perfect balance. That mechanism was proposed in 1967, not by a cosmologist, but by a bomb maker. Andrei Sakharov was the father of the Soviet hydrogen bomb. Sakharov spent days calculating how to release the energy of the sun in a weapon of war. The physicist understood the fundamental forces of nature not as abstract concepts, but as tools of destruction. But in spare moments, Sakharov turned to the early universe. The man looked at the problem of the baryon asymmetry, the excess of matter over antimatter, and formulated three necessary conditions, three rules that any theory of Genesis must obey. These rules are known as the Sakharov conditions. The list forms the checklist for this investigation. Condition number 1, baryon number violation. This violation is the smoking gun. In current particle physics, the number of baryons, protons, and neutrons is strictly conserved. Starting with 5 protons ends with 5 protons. Turning a neutron into a proton preserves the total number. Sakharov realized that for the universe to go from a state of 0 baryons to a state of many baryons, this rule must be broken. A rare unknown interaction must exist that can create or destroy protons. Without this violation, the universe is stuck at 0. The search for this violation has led to some of the most silent places on Earth. Deep inside a mountain in Japan, the Super Kamiokande detector sits in total darkness. This is a tank holding 50,000 tons of pure, distilled water, surrounded by 13,000 golden light sensors, each the size of a large beach ball. These sensors are designed to detect the faintest flash of light. If a single proton among the trillions in the tank were to decay, the event would release a signature flash of blue light, a phenomenon known as Cherenkov radiation. To imagine the scale of this experiment, realize that if a single person in the entire population of the Earth were to sneeze, these sensors would be like the global network waiting to hear that one specific sound. Scientists have watched this tank for decades. The silence is absolute. So far, the detector has seen nothing. Not a single confirmed proton has ever died. But most grand unified theories predict the event happens, just on a timescale of 10 to the power of 34 years, a duration so long that even the stars will have burned out before most protons face their end. So we give condition 1 a pass for now. Condition number 2, charge and charge parity violation. This is the broken mirror. C-symmetry says that physics should be the same if we swap charges. P-symmetry says physics should be the same if we reflect coordinates. Charge and charge parity violation, or CP violation, is the combination. Charge parity violation is often referred to as CP violation. If CP is conserved, then matter and antimatter are treated equally. The pair decays at the same rate. The pair behaves the same way. Sakharov argued that to get an excess of matter, nature must distinguish between the two, a loaded die in the cosmic casino. Condition number 3, departure from thermal equilibrium. This is the escape hatch. Imagine a box of gas that is perfectly hot and perfectly mixed. In this box, for every process that creates a proton, a reverse process occurs that destroys the proton. If the universe stayed in equilibrium, any asymmetry would be instantly washed out by the reverse reactions. Sakharov realized that the universe needed to be changing. The cosmos needed to be expanding and cooling rapidly. This expansion drives the system out of equilibrium, allowing the matter excess to freeze out before the antimatter could catch up and cancel the surplus. These three conditions are the holy grail of baryogenesis. Finding a theory that satisfies all three explains our existence. The third condition is easy. The Big Bang was a rapid expansion. We have the non-equilibrium. The real problem is condition number 2, CP violation, the bias. Science has found CP violation in nature. The phenomenon was discovered in 1964 by James Cronin and Val Fitch at Brookhaven National Laboratory. The team was using the alternating gradient synchrotron, a massive particle accelerator that fired a beam of high-energy protons into a target of beryllium. This collision created a stream of neutral kaons. These short-lived particles are the chameleons of the subatomic world, constantly oscillating between their matter and antimatter states. Cronin and Fitch set up a detector 57 feet away from the source, a distance carefully chosen to allow the short-lived kaons to decay, leaving only the long-lived variety. According to the laws of symmetry, these long-lived kaons should never decay into 2 pions. They should only decay into 3. The team watched as 45,000 kaon decays flashed through their equipment. Out of those 45,000 events, 45 of the particles did the impossible and decayed into 2 pions. This tiny statistical anomaly, just 0.1% of the decays, proved that nature has a preference. The mirror was cracked. More than that, the mirror was fundamentally biased. This discovery was a breakthrough, but the victory was short-lived. Here is the problem. The CP violation found in kaons is tiny. The effect is subtle. When physicists plug this amount of violation into the equations of the early universe, the math yields a baryon asymmetry that is billions of times too small. The standard model, as the theory stands, can explain why some matter exists, but the model cannot explain why this much matter exists. The theory can explain a grain of sand, but not the beach. The gap defines the stakes of the investigation. We are looking for a missing source of CP violation. We are looking for a new particle, a new force, or a new interaction that broke the symmetry in the early universe violently enough to leave behind all the galaxies we see today. Some researchers look toward the standard model extension, a framework that allows for the violation of Lorentz symmetry. The idea that the laws of physics are the same regardless of your orientation or velocity in space. If the universe itself has a preferred direction, that bias could be the engine of our existence. If science cannot find the source, then our understanding of the Big Bang is fundamentally flawed. A huge chunk of the story is missing. The standard model, for all the success, is failing to explain the most basic fact of all. We are here. The universe should be empty. The cosmos should be a cold, dark wasteland of radiation. The fact that space is not empty, the fact that a listener is sitting here breathing, thinking, is the anomaly we are trying to solve. Humanity is the survivor of a cosmic purge. The evidence of how we won is hidden in the debris of the battlefield. To find that evidence, the search must look at the particles that behave the strangest. We must look at the tricksters of the subatomic world, the mesons. And to understand mesons, we have to understand the specific flavor of weirdness the particles bring to the table. The investigation leads to the next chapter, the hunt for the meson clues. Phase 1 of the investigation is complete. We have the motive, survival. We have the crime, broken symmetry. Now we need the weapon. The first suspect is a particle that should not exist for long, but tells us the whole story while the spark of existence endures. The discovery at Brookhaven left the physics world in a state of intellectual crisis. We had found the weapon. We had identified the suspect, the neutral kaon, but we had no idea how the crime was committed. We needed a mechanism. In the early 1970s, the subatomic world felt relatively tidy. Researchers were confident in a framework called the Standard Model. This model was built on a foundation of 4 quarks, up and down, which make up the protons and neutrons in our bodies, strange and charm, the heavier, exotic cousins. For a brief moment, the evidence suggested that these 4 entities were enough to describe the universe. This 4-quark consensus was reinforced by a breakthrough known as the Gaia mechanism, named after physicists Sheldon Glashow, John Iliopoulos, and Luciano Maiani. The math of the trio explained why certain particle decays were rare, and the framework seemed to restore a sense of order to the chaos. The Gaia mechanism was the elegant lock on that door, preventing flavor-changing neutral currents that would have made the subatomic world far more chaotic. Because the math worked so perfectly with 4 quarks, most theorists saw no reason to go looking for more. The community believed the periodic table of the subatomic world was finished. The consensus was more than a technical agreement. The agreement represented a fundamental belief that nature preferred simplicity. Physicists in the 1970s viewed the 4 quarks as 2 complete families. Like a balanced set of scales, these particles seemed to cover every known interaction. To suggest otherwise was to invite unnecessary complexity into a system that had just achieved a first true taste of unity. The confidence in this 4-quark model reached a fever pitch during the November Revolution of 1974. 2 independent teams, one at Brookhaven and another at the Stanford Linear Accelerator Center, simultaneously discovered a new particle called the J-Phi. This entity was the smoking gun for the charm quark. The discovery proved that the subatomic world was organized into neat, predictable families. The success of the Standard Model seemed complete. Nature appeared to be a system of perfect 4-part harmony. But the kaon results from Brookhaven remained like a persistent, annoying leak in a perfect ceiling. The mirror was broken, and the 4-quark Standard Model could not explain why. The discovery remained an isolated anomaly, a piece of evidence that simply refused to fit the 4-quark jigsaw puzzle. This clue takes the investigation to a small office at Kyoto University in 1972. 2 young Japanese theorists, Makoto Kobayashi and Toshihide Masukawa, were staring at the same equations as everyone else. But the pair was looking for a different kind of symmetry. The theorists were looking for a way to let the math break internally. The pair realized that in a world with only 4 quarks, the laws of physics are forced to be symmetric. The mixing matrix, the mathematical grid that describes how one quark transforms into another, is too simple in a 4-quark universe. This grid is restricted to 2 dimensions. In 2 dimensions, every number in the matrix is real. Every interaction is straightforward. No complex phases exist. No imaginary numbers appear. And without an imaginary number in the equations, nature cannot distinguish between matter and antimatter. The math forbids the bias we see in the kaon. To Kobayashi and Masukawa, the conclusion was inescapable. If the 4-quark model cannot explain the broken mirror, then the 4-quark model is wrong. Imagine a high-end audio mixing console. Each slider controls the volume of a specific instrument, but the sliders also determine how the sounds blend together. In a four-quark world, the sliders only move up and down, limited to a flat, two-dimensional plane. This setup creates a clean, predictable sound, but the arrangement lacks the depth of a concert performance. Kobayashi and Maskawa realized that for the symmetry to break, the math needs an extra dimension. The equations need a slider that can also move forward and backward, introducing a complex phase that shifts the timing of the signal. This extra degree of freedom creates an interference pattern between matter and antimatter, allowing one to decay faster than the other. This complex phase acts like a prism, just as a prism takes a beam of white light and reveals a hidden spectrum of colors. The complex phase takes the simple interactions of quarks and reveals a hidden asymmetry. Physicists visualize this asymmetry using a geometric structure called the unitarity triangle. If the laws of physics were symmetric, the triangle would collapse into a flat line. But the complex phase forces the lines to pull apart, creating an interior area that represents the amount of CP violation in the cosmos. To get that phase, to get that prism, you need more than 4 quarks. You need at least 6. Think of this requirement like a tripod. A two-legged stool cannot stand. The object falls flat. A two-generation model forces the math into a flat plane where symmetry is unavoidable. But add a third leg, a third generation, and suddenly the structure gains volume. The triangle opens up. The complex phase appears not as a glitch, but as a geometric necessity. Nature requires complexity to allow for existence. This insight was a radical prediction. In 1973, nobody had seen a 5th quark, let alone a 6th. Nature seemed to have no obvious reason to build a 3rd generation of particles that seemed to have no role in the everyday world. Protons do not need them. Stars do not need them. Humanity does not need them. But the broken mirror demanded them. The theorists postulated 2 new particles, which the scientists dubbed bottom and top. This proposal was not a minor addition. The theorists were doubling the complexity of the subatomic world based on a single mathematical requirement for asymmetry. They were claiming that the universe is built of 3 families of quarks, organized in pairs of increasing mass. For the next 20 years, the physics world went on a hunt. The bottom quark was the first to fall. In 1977, a team at Fermilab, led by Leon Lederman, discovered a resonance in the data from a high-energy proton beam. They called the particle the upsilon. The finding was the proof of the 5th quark. The 3rd generation was real. But the 6th quark, the top quark, was a different story. This particle was the ultimate ghost. Theorists expected the particle to be heavy, but nature had a surprise in store. As the years passed and the accelerators became more powerful, the top quark remained hidden. Each failure to find the quark raised the stakes. If the top quark did not exist, then the Kobayashi-Maskawa mechanism was a failure. If the top quark did not exist, we were back to square one with the kaon mystery. The hunt lasted until 1995, for 2 decades. Physicists at Fermilab smashed protons and antiprotons together, searching for a ghost that refused to appear. The machine the team used, the Tevatron, was a 4-mile ring of superconducting magnets buried beneath the Illinois prairie. This device was the most powerful accelerator of the time, a sledgehammer designed to crack the vacuum. When the top quark finally emerged from the debris, the mass was staggering. This single subatomic particle weighs as much as an entire atom of gold. This entity remains the heaviest fundamental particle ever discovered. The existence of the top quark confirmed the genius of the Japanese theorists. The 3x3 grid was complete. The complex phase was real. In 2008, Kobayashi and Masukawa were awarded the Nobel Prize in Physics, cementing the CKM matrix as the map of the quark world. By adding these two rows to the matrix, the math changed. Suddenly, the algebra allowed for a single, complex phase to remain, one imaginary number that cannot be rotated away. This single number, this ghost in the machine, is the source of all CP violation in the standard model. This phase is the mathematical bias that allows matter to act differently than antimatter. We call this grid the CKM matrix, the Kabibo-Kobayashi-Masukawa matrix. This structure is the map of the quark world, and for a while, the matrix seemed like the complete answer. But the investigation did not stop at kaons. If this complex phase exists, the bias should show up in other particles too. The asymmetry should show up in the heavier cousins of the kaon. The violation should show up in particles containing the charm quark. For decades, the search continued, and for decades, the search found nothing. The charm quark is heavy. This particle spins differently. The internal interactions of the quark are faster. The theoretical predictions for CP violation in charm decays were tiny. Most physicists thought the world would never see the effect. The deviation was too small to measure. The signal was buried in the noise of the strong nuclear force. But the LHCb experiment at CERN is designed to find needles in haystacks. This massive detector, located 100 meters underground, stands 10 meters high and 20 meters long. The facility is a precision instrument, filtering through billions of collisions every second to find the rarest events in nature. And in 2019, the team pulled off a measurement that many thought was impossible. The team looked at D0 mesons. A D0 is like a heavy version of the kaon. This particle contains a charm quark and an up antiquark. Like the kaon, the D0 can decay into pairs of particles. The meson can decay into a positive kaon and a negative kaon, or the particle can decay into a positive pion and a negative pion. To distinguish between these final states, the experiment relies on a technology called ring imaging Cherenkov detectors, or RICH, as the pions and kaons fly through the detector at speeds faster than light in that specific medium. The particles emit a cone of blue light. By measuring the angle of this cone, the investigators can calculate the velocity of the particle. Combined with momentum data from the magnets, this allows the team to identify the exact identity of the daughter particles with near-perfect certainty. To capture the whisper of the raw signal, the LHCb detector uses a device called the vertex locator, or VEL. Imagine a series of silicon sensors positioned just millimeters away from the proton beam. As particles are birthed in the collision, these sensors track the flight paths with a precision of 10 micrometers. This accuracy is equivalent to measuring the width of a human hair from a distance of several football fields. By tracing the tracks back to the origin, the investigators can distinguish between the initial collision and the decay of the D0 meson a fraction of a millimeter later. The engineering of the VLO is a masterclass in extreme physics. The sensors must survive in a vacuum while being bombarded by 1 trillion particles every second. These silicon plates are cooled to negative 30 degrees Celsius using a complex circulation of liquid coolant to prevent the intense radiation from melting the electronics. The danger here is palpable. The sensors are positioning themselves a fraction of an inch from a beam carrying enough energy to melt a block of copper instantly. To protect the delicate silicon, the system uses a beam dump protocol. If the magnets lose control of the protons for even a microsecond, the entire beam is magnetically kicked out of the ring and into a massive block of graphite and concrete, absorbing the energy before the machine's destruction. The VELO is not just a camera. The device is a daredevil sitting on the tracks of a runaway train. More impressively, the two halves of the detector are retractable. The jaws sit open like a set of gates, while the Large Hadron Collider stabilizes the beam, and then the mechanisms close to within 8 millimeters of the racing protons. This proximity allows the investigators to see the secondary vertex, the exact point where a D0 meson vanishes and the daughter particles of the meson appear. Without this mechanical precision, the subatomic clues would be lost in the blur of the primary collision. This precision is supported by a trigger system that operates at the speed of light. Every second, 40 million bunches of protons collide within the detector. Each collision creates a spray of secondary particles. The computer systems have less than a microsecond to decide which events to keep and which to discard. This effort is an investigation conducted at the limit of human technology, where the clues vanish in the blink of an eye. The data volume is so massive that the researchers must discard over 99% of the events, searching for the statistical whisper that reveals the broken mirror. The investigators asked a simple question: does the D0 meson decay into these final states at the same rate as the anti-D0? The researchers sifted through millions of collisions. Every vertex was reconstructed with the incredible precision of the silicon sensors. The team counted the pions. The team counted the kaons. The anomaly in the charm sector represents a fundamental challenge to our understanding of the strong force. Unlike the strange quark, the charm quark exists in an environment where the internal dynamics are dominated by massive, heavy quarks. This environment creates a different setting for the CKM phase to manifest. The search involved more than a simple number. The scientists were looking for proof that the broken mirror is a universal feature of the standard model. And the scientists found a difference. The measurement was called delta ACP. This value represents the difference in the asymmetry between the two decay modes. If CP symmetry was perfect in the charm sector, this number should be 0. The result was negative 15.4 times 10 to the power of negative 4. That number is 0.00154. The value is a whisper, a tiny deviation. But with the massive amount of data from the Large Hadron Collider, the statistical significance reached 5.3 sigma. In particle physics, 5 sigma is the gold standard. This metric means the odds of this being a random fluctuation are less than 1 in 3 million. To visualize this, imagine 2 synchronized swimmers diving into a pool. If symmetry were perfect, the divers would splash the water at the exact same millisecond. But in the charm sector, 1 swimmer is late. The delay is infinitesimal, a fraction of a heartbeat of a gnat, but the delay is there. And in the strict rules of quantum mechanics, that delay is a violation of the law. The investigators were tempted to declare the case closed. We have the violation. We have the mechanism. We have the Nobel Prizes. We explain the universe. Right? No. The investigation takes a dark turn at this point. The pieces stop fitting at this point. We have CP violation. We have a bias, but we can calculate how much bias the CKM matrix actually provides. We can plug the numbers into the equations of the early universe. We can simulate the Big Bang. We can ask, if we start with equal amounts of matter and antimatter, and we let the CKM matrix perform the task. How much matter is left over? The answer is devastating. The standard model predicts a baryon asymmetry of about 10 to the power of -20. Remember the number we need. We see a universe with an asymmetry of 10 to the power of -10. Do the math. 10 to the power of -20 is 10 billion times smaller than 10 to the power of -10. The mismatch is far more than a rounding error. The discrepancy is a catastrophe. A baryon asymmetry of 10 to the power of -20 means that for every 10 trillion particles of matter, only one should have survived. The universe we see, the universe of stars and galaxies, is 10 billion times richer in matter than the standard model allows. We are missing 99.99999% of the source of our existence. To understand the scale of this failure, imagine searching for a specific grain of sand on a beach. You find the grain you celebrate, but then you look up and realize the beach is not a mile long. The beach is the size of the entire galaxy. The standard model explains the grain. The model fails to explain the rest of the galaxy. We are not missing a small piece of the puzzle. We are missing the entire box. The CKM matrix is perfect for what it does, but asking the matrix to explain the universe is like asking a candle to light up a stadium. The standard model explains 1/10 billionth of the matter in the universe. This theory explains a single grain of sand on a beach that stretches for miles. If the CKM matrix was the only source of asymmetry, the annihilation would have been nearly total. Galaxies would not exist. Stars would not exist. Planets would not exist. Humanity would not exist. The universe would be empty. The chasm is the gap. The chasm separates our theory from our reality. We have found the mechanism for asymmetry, but the mechanism is too weak. This effort is like trying to empty the ocean with a teaspoon. The process is correct, but the scale is wrong. This reality implies a conclusion that is terrifyingly simple. Another source must exist. Another broken mirror must exist. Another particle, another force, or another interaction must violate CP symmetry, but a violation must be violent. This source must be stronger than the CKM matrix. This source must be hidden in a part of physics we have not yet explored. We call this new physics, but this term is just a polite way of saying the experts do not know what is going on. The investigation now shifts gears. We can no longer rely on the kaons. Those particles have told their story. We can no longer rely on the standard charm decays. Those events are following the rules of the weak CKM matrix. We need to look for a mechanism that breaks the CKM rules. We need to find a discrepancy within the discrepancy. The investigation leads deeper into the subatomic world. We must look beyond the simple mesons. We must look at the heavy lifters of the particle world. The quest for the missing mirror break is moving toward the most complex structures nature allows. The kaons whispered the truth. The charm quarks confirmed the mechanism, but the math screams that we are still missing the main event. Somewhere, hidden in the interactions of the heaviest particles, or perhaps in the behavior of the neutrino, lies the true engine of creation. The standard model is a beautiful map, but the drawing is a map of a ghost town compared to the reality we inhabit. The next chapter reveals how the search turned from the lightness of quarks to the weight of existence. The investigation into the missing mirror of the universe entered a new electrified phase in the spring of 2025. For decades, the physics community had been staring at a wall. The Kamens and the Mesons had provided a mechanism, a mathematical bias, but that bias was 1 billion times too small to explain why a single galaxy exists. The investigation went cold. For years, the Large Hadron Collider sifted through the debris of billions of collisions, finding only the subtle whispers of the CKM matrix. But the researchers at CERN knew that mesons, which are particles made of just a quark and an antiquark, might be too simple to carry the secret of cosmic origin. The hunt shifted toward the heavyweights of the subatomic world. The investigators turned their attention to baryons. Baryons are the building blocks of the visible world. Every atom in every star and every human body is a baryon. If nature has a fundamental bias, the most logical place to look for that bias is in the very particles that make up the matter of the universe. Unlike mesons, which vanish almost as soon as the particles are created, baryons are the survivors. But finding a broken mirror in a baryon had been the holy grail of particle physics for 60 years. Every experiment, from the first kaon discovery in 1964 to the modern era, had failed to find a definitive signal. That changed when the LHCb Collaboration released the results of the search into the decay of the lambda baryon. The entity is more than 5 times heavier than a proton, containing a bottom quark, an up quark, and a down quark. Because the particle contains the heavy bottom quark, the lambda b acts like a laboratory for the most extreme interactions the standard model allows. In March of 2025, the investigators at CERN announced that the team had finally seen the signal. The reality was now a measured fact. The team focused on a specific, complex decay path. The investigators tracked the lambda b as the particle transformed into a proton, a negative kaon, and a pair of pions, one positive and one negative. While the LHCb detector relies on the precision instruments we encountered during the search for mesons, tracking a baryon decay requires a leap in complexity. In the meson studies, investigators looked at two-body decays, a relatively simple split where one particle becomes two. But the lambda baryon undergoes a chaotic 4-body decay, exploding into a proton, a kaon, and 2 pions. Imagine trying to reconstruct a car accident where only 2 vehicles are involved versus a 4-car pileup. The geometry is vastly more complex. The investigators must track the energy and momentum of 4 distinct daughter particles simultaneously, ensuring that every trajectory traces back to the exact same point in space and time. The accuracy is critical because the lambda baryon travels only a few millimeters before the entity vanishes. To see the secondary vertex, the point where the baryon transforms, the vertex locator must distinguish a distance smaller than the thickness of a human hair. Any error in the tracking of the 4 daughter particles would blur the signal, making the detection of the asymmetry impossible. The researchers are building a high-speed, 3-dimensional movie of the most crowded intersection in the universe. Reconstructing this 4-car pileup requires a level of geometric precision that pushes the technological limits of silicon. While the VELO system provided the primary tracking in the meson studies, the baryon breakthrough demands a more complex mapping of the subatomic debris. Each silicon plate must capture the trajectory of the proton, the kaon, and the 2 pions with enough accuracy to calculate the precise angle of their flight. The effort is not a simple snapshot. The researchers are solving a multi-dimensional geometry problem in real time. The sensors must distinguish between 1 billion possible paths to find the one configuration that originated from a single lambda b decay. The reconstruction is the only way to build the Dalitz plots that reveal the hidden bias. Mapping the energy of 4 distinct particles into a single coherent image is like trying to trace the individual ripples in a pool after a handful of gravel has been thrown in. The task requires more than simple speed. The challenge is one of resolution. Without the ability to pinpoint the origin of each daughter particle within 10 micrometers, the subtle signal of the broken mirror would vanish into a blur of secondary collisions. The precision is the silent engine of the 2025 discovery. The data revealed a staggering truth. The lambda baryon and the anti-lambda baryon do not decay at the same rate. When the investigators compared the two, the researchers found a difference that defied the old laws of symmetry. Reaching a statistical significance of 5.2 sigma, the finding stands as a major milestone. The metric is the gold standard of physics, representing less than a 1 in 3.5 million chance that the observation is a fluke. The broken mirror had finally been spotted in the very heart of the matter that builds the universe. To understand why this discovery is so profound, imagine a master watchmaker who builds 2 identical clocks. Every gear is identical. Every spring is wound to the same tension. In a symmetric world, these 2 clocks should tick in perfect unison for eternity. But when we look at the baryon world, we find that one clock ticks slightly faster than the other. The gears inside the lambda B move with more than simple difference. The mechanism operates with a fundamental bias. The bias is not a mistake in the construction of the clock. Instead, the asymmetry is a fundamental property of the metal. The internal complexity is the key. Mesons are like a simple stopwatch with only 2 gears. The interactions are limited. But a baryon is like a grandfather clock, filled with a complex arrangement of pendulums, weights, and intermeshing wheels. With 3 quarks instead of 2, the baryon has more ways to interact. More degrees of freedom exist. More ways for the complex phase of the CKM matrix to interfere with the strong nuclear force. The interference is where the asymmetry resides. The discovery sent a shockwave through the physics community. Most theorists expected the signal to be even smaller, perhaps too small to see even with the power of the Large Hadron Collider. But the lambda B showed an asymmetry that was bold and clear. The question shifted from whether baryons violate CP symmetry to the specific mechanism driving the asymmetry. The search for a mechanism led the investigation to the work of 2 prominent theorists, Fu-Sheng Yu and Tai-Dian Lu. As the data from CERN began to accumulate, these researchers realized that the standard model was hiding a secret within the strong nuclear force. Before 2025, the community believed that CP violation was a purely weak force phenomenon. In the old model, the strong force was seen as a neutral background, a silent stage where the quarks performed their transformations. But the lambda B results proved that the stage was rigged. The old way of calculating asymmetry was incomplete. The old models treated particle decay as a clean one-step process. A particle exists, a particle decays, and the story ends. The view was a luxury of the Meson world, where the internal dynamics are simple, but the baryon world is messy. The baryon world is dense. In a system with 3 quarks, the strong nuclear force is constantly pulling and pushing, creating a chaotic environment where the simple rules of the CP matrix are amplified by the presence of other particles. Yu and Lu proposed a more messy, more realistic mechanism. The pair focused on a process called NP rescattering. In this model, the decay is not a single event. The process is a conversation. When the lambda B transforms, the daughter particles do more than simply fly away into the void. Instead, the proton and the pion spend a fraction of a second interacting with each other. The particles scatter. These daughters bounce. Consequently, the entities exchange energy through the strong nuclear force. This conversation is known as a final state interaction. These interactions are critical because the interactions provide the strong phase required for the broken mirror to manifest. Remember that the CKM matrix provides the weak phase, the mathematical bias. But for that bias to result in a physical difference in decay rates, nature needs a second phase. Nature needs a strong phase that comes from the physical environment of the decay. The ENP rescattering provides that environment. The pions and the protons act like a resonant chamber, amplifying the subtle bias of the weak phase into a measurable signal. Think of this mechanism like an acoustic guitar. The strings represent the weak phase of the quarks. When you pluck a string, the string vibrates at a specific frequency, but the sound of the string alone is quiet and thin. To make music, the instrument needs a body. The wooden chamber vibrates in response to the string, amplifying the sound and giving the sound a distinct character. The ENP rescattering is the wooden body of the guitar. Without this resonant chamber, the fundamental bias of the quarks would remain a silent mathematical abstraction. The final state interactions take the quiet whisper of the weak phase and turn the whisper into a roar that the detectors at CERN can hear. Yu and Liu developed a new theoretical method to calculate these effects. The pair used experimental data from nucleon scattering, the way protons and pions behave when the particles collide, to predict how the lambda B would decay. These calculations matched the LHCb results with incredible accuracy. The link to baryogenesis is a hint that the investigators finally understood the engine of the baryon breakthrough. The strong force served as more than background noise. The force acted as an active participant in breaking the symmetry of the universe. But this mechanism is notoriously difficult to calculate. Baryons contain 3 quarks, which means the strong force is interacting in a 3-way tug of war. Unlike mesons, where the force is a simple line between 2 points, the baryon is a complex web of gluons. This complexity means that even small uncertainties in the mass or the width of excited nucleon states can throw the whole calculation into chaos. The breakthrough by Yu and Liu was finding a way to bypass these uncertainties, using raw scattering data to ground the theory in reality. The link to biogenesis is the real stakes of the investigation. If we can understand how baryons break the mirror in the lab, we might finally understand how the early universe broke the mirror during the Big Bang. The Anpai rescattering mechanism is a hint that the path to existence is found through complexity, not simplicity. Nature did not choose a clean, symmetric path. Nature chose a messy, resonant, and biased path. As the investigators dug deeper into the lambda B data, the team discovered a signal even more puzzling. The asymmetry was not spread evenly across the decay. The broken mirror did not appear as a constant bias in every collision. Instead, the asymmetry was localized. The complexity is captured through the use of Dalit's plots. These mathematical maps represent the phase space of the decay, plotting the mass of the particles against the energy of the particles. The maps revealed hotspots of asymmetry. In certain regions of the phase space, where the particles have specific energies and angles, the CP violation was massive. In other regions, the symmetry remained nearly perfect. When the team focused on these resonant regions, the significance of the signal jumped from 5.2 sigma to a staggering 6.0 sigma. The result was no longer a hint. The result was a smoking gun. To understand this localization, we have to look at the interference of subatomic waves. In the quantum world, particles represent more than solid balls of matter. The entities are waves of probability. When a lambda baryon decays, the daughter particles can travel along multiple overlapping paths at the same time. These paths represent different quantum states, and like ripples in a pond, these waves can interfere with each other. In some regions of the phase space, the waves are out of phase. The peaks of one wave meet the troughs of another, and the asymmetry cancels out, leaving a region of perfect symmetry. But in the resonant regions, the waves are in sync. The peaks of the matter wave and the peaks of the antimatter wave reinforce each other, creating a storm of CP violation that is visible to the detectors at CERN. This constructive interference is what creates the hot spots in the Dalitz plot. The asymmetry is not a constant property of the particle. The asymmetry is a dynamic result of how these quantum waves mesh together during the final moments of the decay. Imagine standing in a large cathedral. If you speak in a normal voice, your words might be lost in the vastness of the space. The sound is diffuse, but if you stand in a specific spot under a dome, your voice is captured and focused. The architecture of the dome reflects the sound waves back to a single point, making your whisper sound like a shout. Similarly, the resonant regions of the lambda B decay mimic the dome of that cathedral. These specific regions act as the whispering galleries of the subatomic world. The geometry of the decay focuses the subtle bias of the quarks, making the asymmetry visible only when the particles are in the right place at the right time. The localization is a clue that the investigation is on the right track. If the asymmetry were just a random error, the asymmetry would be spread out like noise across the whole map. But the hot spots align perfectly with the predictions of the OnPy rescattering model. The locations of the asymmetry tell us where the resonance is strongest. The locations tell us exactly where the pions and protons are having their most intense conversations. The discovery raises a new mystery. Why does nature only allow the mirror to break in these specific resonant corners? Is the localization a hint of a deeper law, or is the localization just a mechanical byproduct of the way quarks are bundled together? The search for the answer requires a comparison between the baryons and the mesons. We have to ask why the heavy lifters of the universe are so much more revealing than their lighter cousins. The difference between a meson and a baryon is more than just the count of their quarks. The difference is a fundamental shift in the architecture of matter. A meson is a two-body system, a quark and an antiquark bound by a string of gluons. A baryon is a three-body system. The extra quark changes the entire framework. The spin, the structure, and the angular momentum of a baryon are vastly more complex. In a meson decay, the angular momentum is relatively simple. The particles fly apart in a way that is easy to track. But in a baryon decay, the particles have non-zero spin. This spin means the daughter particles can come out in different angular momentum configurations. Physicists call these configurations L0 and L1. The breakthrough in 2025 was the realization that these different configurations can actually work against each other. In some baryon decays, like the transformation of a lambda B into a proton and a pion, the asymmetry from the L0 path and the L1 path can be large, but the paths have opposite signs. One path biases toward matter and the other biases toward antimatter. When you measure the whole decay, the two paths cancel each other out. The total asymmetry looks like zero. The mirror appears to be intact, even though the mirror is actually broken twice. To visualize this hidden war, imagine two competing melodies playing in the same room. If the melodies are out of tune, the resulting sound is chaotic. But if the melodies are perfectly inverted, they can cancel each other out, leaving only silence. For decades, investigators were hearing that silence. The investigators believed the mirror was unbroken because they were only measuring the total volume of the room. But the LHCb detector allowed the researchers to isolate the individual melodies. The team found that the music of the subatomic world is not silent. The melody is filled with a loud, aggressive bias that simply hides behind the complexity of the baryon. The destruction of asymmetry is a phenomenon that does not occur in mesons. Mesons do not have the internal spin structures to create this kind of cancellation. The reality explains why some earlier baryon experiments found nothing. The 2025 discovery succeeded because the four-body decay allowed the researchers to separate these different configurations. The team could see the bias because the team had a more detailed map. Think of a three-legged stool versus a two-legged stool. A two-legged stool is inherently unstable in a three-dimensional world. The stool can only exist in a flat plane. A meson is like that two-legged stool. The meson is restricted by the simplicity of the meson, but a baryon with three quarks is like a three-legged stool. The structure gains volume. The stool can stand without support. The extra leg provides the stability and the complexity needed for the complex phase of physics to manifest in new ways. Ultimately, the baryon represents more than a heavier particle. The entity is a more complete representation of the laws of nature. The complexity brings the investigation back to the Sakharov conditions we encountered earlier. Andrei Sakharov argued that for the universe to survive, the laws of physics must distinguish between matter and antimatter. The condition is the CP violation. But Sakharov also realized that the universe must be out of equilibrium. The universe required a mechanism to lock in the matter surplus before the antiparticles could re-engage and erase the whole surplus. The resonant regions act like a cosmic filter, trapping the surplus of matter in a way that the simpler mesons cannot achieve. Ultimately, the complexity of the baryon is what makes the baryon the real key to the matter dominance of the universe. If we existed in a universe made only of mesons, we would not exist. The simplicity of the meson world is too symmetric. But we exist in a baryon world. We are built of three quark bundles that have the internal machinery to break the mirror and survive the primordial fire. The lambda B results suggest that the bias that allowed us to exist is a direct result of this three-quark complexity. The breakthrough of 2025 has opened a new horizon. Furthermore, the investigators at CERN have proved that baryons violate CP symmetry, and the team has identified a mechanism, the resonant rescattering of pions and protons, that explains how the asymmetry occurs. But the case is far from closed. Even with these new baryon results, the total amount of asymmetry we have found is still too small to explain the entire universe. The baryon breakthrough is a massive piece of the puzzle, but the baryon breakthrough is not the whole picture. Somewhere, another source must exist. Another hidden asymmetry is waiting to be found, and the search for that missing mirror break is now moving into the most sensitive experiments ever devised. The quest takes the investigation away from the high-energy chaos of the Large Hadron Collider and toward the quiet, precision world of the antimatter traps. In these facilities, researchers are not smashing particles. Instead, the investigators are cooling them to near absolute zero, trapping them in magnetic cages to perform the ultimate mirror test. The shift in strategy is critical. If we cannot find enough asymmetry in the way baryons decay, we must look at their fundamental properties. We must ask if an atom made of antimatter behaves exactly like an atom of matter. The search means building antihydrogen from antiprotons and positrons. The investigation requires using laser spectroscopy to measure the energy levels of the anti-world to parts in a trillion. The investigators are hunting for a deviation in the spectrum, a tiny shift in the light that would prove that the mirror is fundamentally flawed. Beyond antihydrogen, the researchers are even looking toward antideuterium, the heavier form of antimatter, containing both an antiproton and an antineutrino, represents a new frontier in the search for cosmic bias. To understand the stakes of the shift, imagine a forensic investigator who has reached the end of the evidence at a primary crime scene. The investigator has sifted through the wreckage, but the weapon is still missing. The forensic reality forces the investigator to widen the perimeter. The investigator must look for the weapons that nature has hidden in the deep freeze of the vacuum. If the Large Hadron Collider is the sledgehammer of physics, these precision traps are the scalpel. To find the final answer, we must stop smashing particles together and start looking at the particles one at a time. We must look at the antihydrogen mirror. The Lambda B discovery has given us a new map. The finding has shown us that the strong force is a key player in the cosmic bias. More than that, the discovery has shown us that the resonant regions of the subatomic world are where the truth is hidden. But most importantly, the discovery has shown us that the universe is not a perfect mirror. The universe is a system that prefers existence over nothingness, and the universe uses the complexity of the baryon to make that choice. The investigation continues. After all, the stakes remain the same. Why are we here? The baryons have given us the first clear answer in 60 years. The mirror is broken, and we are the pieces that fell through the cracks. The next step is to see if that break is as deep as the standard model predicts, or if nature has one more surprise waiting for us in the absolute stillness of the antimatter labs. The path from kaons to charm to baryons has revealed a consistent pattern of bias. Each step has confirmed that the Kobayashi-Maskawa mechanism is a real force in nature. But each step has also highlighted the gap between what we can explain and what we observe in the stars. The baryon breakthrough in 2025 is a milestone, a moment where the investigation finally broke through the wall of the Meson world. The discovery has provided the first evidence of symmetry, breaking in the very matter that builds our reality. Our investigators are now focused on the future. With more data from the upcoming runs of the Large Hadron Collider, the team expects to find even more baryon asymmetries. The team expects to see the broken mirror in charm baryons and other exotic states. Every new observation is a data point in the quest to solve the origin of the universe. The Lambda B result is the first light of a new dawn in particle physics. The mystery of the missing asymmetry remains the primary challenge of modern science. But for the first time in a generation, the researchers have a new lead. They have a new mechanism. They have a new horizon. The investigation into the baryon breakthrough shows that the mirror has done more than simply break. The symmetry has shattered in a way that allows us to exist. The discovery is the first step toward finding the missing 99% of the cosmic story. The mystery now turns elsewhere. This new path leads the investigation away from the violent collisions of the Large Hadron Collider and toward the silent, frozen chambers of the antimatter traps, while the search for decaying baryons reveals how matter might have gained an edge through chaos. Another group of researchers is asking a more fundamental question. These investigators want to know if the reflection is flawed. Scientists have long assumed that matter and antimatter are perfect mirror images of each other, governed by a rule known as CPT symmetry. The history books say that this symmetry is the ultimate law of the universe, an unbreakable foundation that ensures every particle has an identical twin with opposite charge. But as we look closer at the evidence from the anti-hydrogen laser physics apparatus, known as ALPHA experiment at CERN, the pieces do not quite fit the expected narrative. If this symmetry is truly perfect, then the existence of our matter-dominated world remains an impossible crime with no weapon. The concept of symmetry has always been the North Star for physicists. In 1918, the German mathematician Emmy Noether proved that every symmetry in nature is linked to a conservation law. Noether demonstrated that if a physical system behaves the same way regardless of the location in space, momentum must be conserved. If the system behaves the same way regardless of the orientation, angular momentum must be conserved. And crucially, if the laws of physics do not change over time, energy must be conserved. These findings provided the first rigorous framework for understanding why the universe behaves with such regularity. The theorem of Noether transformed symmetry from an aesthetic preference into a mathematical necessity. Before these discoveries, researchers viewed the consistency of nature as a happy accident. After Noether, the community realized that the structure of space-time is built on these hidden balances. The theorem remains one of the most profound insights in the history of human thought, linking the geometry of the universe to the physical laws that govern our reality. By the middle of the 20th century, the investigation into symmetry moved from the macroscopic world into the subatomic world. Researchers identified three specific transformations that seem to govern the behavior of particles. The first is charge conjugation, denoted by the letter C. This process involves replacing every particle with the corresponding antiparticle. For example, a negative electron becomes a positive positron. The second is parity, or P, which involves reversing the spatial coordinates. This transformation is equivalent to looking at a physical process in a mirror, where left becomes right and right becomes left. The third is time reversal, or T, which means playing the movie of a physical interaction backward. While investigators were shocked to discover in the 1950s and 60s that nature could break charge and parity individually, the combination of all three was believed to be absolute. The CPT theorem, developed by Wolfgang Pauli, Gerhard Luders, and Richard Jost, states that any local quantum field theory that obeys relativity must be invariant under the combined operation of C, P, and T. This triplet represents the ultimate mirror, a perfect reflection, where every subatomic process is identical regardless of the direction of time or the charge of the particles. To understand why CPT symmetry is considered the ultimate rule, imagine a high-definition film of a subatomic reaction. If a researcher takes this film, reverses the colors to swap matter for antimatter, flips the image in a mirror, and then plays the reel backward, the resulting movie should look exactly like a valid physical process. The laws of physics should not be able to distinguish the original from this triple inverted version. The rule constitutes a fundamental necessity for the consistency of the cosmos. If a single experiment found a violation of CPT symmetry, the entire framework of modern physics would collapse. The concepts of causality, where causes always precede effects, and relativity, where light speed is the absolute limit, would require a total rewrite. Consequently, every test of this symmetry is a high-stakes inquiry into whether our understanding of reality is built on a stable foundation. The mirror must be perfect, or the very structure of logic in the universe would begin to unravel. The mystery deepens when we consider the implications for the early universe and the problem of baryogenesis. If CPT symmetry is perfect, then every property of matter and antimatter must be identical. The mass of a proton must be exactly equal to the mass of an antiproton. The magnetic moment of a positron must be exactly equal but opposite to the magnetic moment of an electron. Most importantly, the energy levels of an atom made of antimatter should perfectly match the energy levels of an atom made of matter. But if these twins are truly identical in every way, then the Big Bang should have produced these twins in exactly equal amounts. Matter and antimatter would have emerged from the primordial furnace, met in the void, and annihilated back into pure radiation. The fact that galaxies, stars, and human observers exist is a screaming signal that somewhere, somehow, the symmetry failed. The discrepancy creates a profound tension in the investigation. The standard model requires the mirror to be perfect, but the visible universe is proof that the mirror is broken. We occupy the gap between a mathematical proof of equality and the physical evidence of bias. The Alpha experiment brings the investigation to the facility at CERN, while the Large Hadron Collider uses brute force to smash particles. The Alpha team uses precision to build atoms. The objective is to create antihydrogen, the antimatter version of the simplest element in the cosmos. Regular hydrogen consists of a single proton orbited by a single electron. Antihydrogen consists of a single antiproton orbited by a single positron. Because hydrogen is the most well-understood system in physics, building the antimatter version allows for the most precise comparison possible. If the investigators find even a tiny difference in the way antihydrogen behaves, the mystery of our existence might finally have a solution. The effort is one of the most difficult technical challenges in the history of science. Antimatter cannot touch the walls of any container made of matter, or the sample will vanish in a flash of pure energy. The researchers must operate in an environment where the slightest error leads to total erasure. To solve this problem of containment, the investigators build magnetic cages. The process begins in the antiproton decelerator, a circular ring at CERN that takes antiprotons created in high-energy collisions and slows these antiprotons down. But these antiprotons are still too hot for trapping. The team uses a second ring known as extra-low-energy antiproton, or ELENA, to cool the particles further, reducing the energy until the antiprotons move at a crawl. These cold antiprotons are then nudged into a Penning-Malmberg trap, where powerful superconducting magnets and electric fields hold the particles in a vacuum colder than the space between galaxies. Once the antiprotons are secure, the researchers introduce positrons, which are created by the radioactive decay of sodium-22. When these two species meet in the heart of the trap, the particles can bond to form neutral antihydrogen. The complex synchronization requires the absolute alignment of magnetic fields and electric pulses to ensure that the newly formed atoms do not simply drift away and annihilate. The real challenge begins once the antiatoms are formed. Because antihydrogen is neutral, electric fields can no longer hold the atoms in place. Researchers must rely on the tiny magnetic moment of the antihydrogen. To achieve this, the team builds an octupole magnetic field, a complex arrangement of magnets that creates a magnetic minimum in the center of the trap. Such antihydrogen atoms are attracted to this minimum, becoming suspended in a magnetic bottle. These traps allow the researchers to hold the antiatoms for minutes or even hours, long enough to perform the ultimate test. Laser spectroscopy is the art of measuring energy by observing how atoms interact with light. Every atom has a unique set of energy levels, like the rungs on a ladder. When a laser pulse hits an atom with the exact right frequency, the positron or electron jumps from one rung to another. By tracking these jumps, the investigators can map the soul of the anti-atom. The alpha experiment focuses on two primary transitions. One transition is the 1s to 2es transition, a narrow and stable jump that allows for extreme precision. Another is the 1s to 2p transition, which involves the absorption of ultraviolet light at a wavelength of 121.6 nanometers. This specific wavelength is known as the Lyman alpha line. Measuring this line in antihydrogen is a way of checking the serial number of the anti-atom to see if the identity matches the matter version. If the frequency required to trigger this jump in antihydrogen is even slightly different from the frequency in regular hydrogen, the mirror is flawed. The investigators are looking for a shift of just a few parts in a trillion. To achieve this resolution, the team must account for every possible source of error, from the vibration of the CERN facility to the subtle influence of the magnetic fields used to hold the atoms. The researchers are essentially building a laboratory that is more precise than nature. Think of this process like tuning a musical instrument to a very distant and faint reference note. Regular hydrogen is the master tuning fork, vibrating at a specific, known frequency. Antihydrogen is the mysterious instrument from the anti-world. The investigators at CERN are slowly turning the dial of their laser, looking for the exact point where the anti-atoms resonate. Because the transition is so sharp, even a tiny deviation in the frequency would be obvious. The researchers are essentially asking if the strings of the universe are tuned the same way for matter and antimatter. This resolution is comparable to determining the exact position of a single grain of sand across the width of the Atlantic Ocean. The level of resolution is necessary because the standard model predicts that the frequencies should be identical. Any measured difference would be a sign of new physics, a breakthrough that would explain why substance exists rather than a void. In 2024, the Alpha Collaboration, including researchers like Arnaldo Vargas from the University of Puerto Rico, pushed this technique to a new limit. The team reported the results of the 1s to 2p transition measurements, comparing the data to the established values for regular hydrogen. The resolution was high enough to detect the most subtle deviations predicted by theories that go beyond the standard model. But here is the thing that makes the mystery even more frustrating. The results showed that the antihydrogen spectrum matches the hydrogen spectrum perfectly. Every measurement, every jump, and every energy level aligned with the predictions of CPT symmetry to within the limits of the instruments. The investigators found no bias. The mirror appeared to be flawless. This confirmation of symmetry is a triumph for the standard model, but the perfection is a major setback for the search for cosmic origin. The pieces of the puzzle still do not fit the reality of our existence. While this result is a massive victory for the standard model, the finding leaves the original mystery of cosmic origin unsolved. If matter and antimatter are this identical, then the reason for our existence remains hidden in a shadow that our lasers cannot yet reach. The search for a flaw in the reflection has confirmed that the reflection is the most accurate measurement humans have ever achieved. The team established that the frequencies are consistent to parts in a trillion. The level of agreement establishes the most stringent constraints ever placed on Lorentz and CPT violation in the antimatter sector. Arnaldo Vargas used these findings to set bounds on 26 different effective coefficients within the standard model extension. The extension is a mathematical map of all the ways that relativity and symmetry could potentially fail. By establishing these bounds, the researchers have narrowed the search area for the missing asymmetry, forcing the investigation to look toward even more exotic and hidden corners of physics. Each coefficient in this map represents a specific type of bias. Some coefficients describe a preference for a certain direction in space, while others describe a difference in the way particles respond to gravity or time. By showing that antihydrogen behaves exactly as predicted, the researchers have ruled out a vast field of alternative theories. The case for CPT symmetry has never been stronger. However, the contradiction suggests that the missing asymmetry is not a property of the building blocks themselves, but a property of how the building blocks interact in the extreme environment of the early universe. The investigators are left with a mystery that seems to hide only when we look at the puzzle directly. The investigators are left with a smoking gun that leaves no fingerprints on the weapon. We know the bias exists because we are here to measure the results. But every time we look at the individual pieces of the anti-world, the pieces appear perfectly fair. The mystery has shifted from finding a flaw in the particles to finding a flaw in the way the particles were assembled. The contradiction leads to the most complex phase of the alpha investigation. As the researchers push for even higher precision, the team is hitting the fundamental limits of the technology. Building a perfect magnetic trap is impossible. The fields are always slightly inhomogeneous, meaning the magnetic strength varies from one point to another within the trap. This variation shifts the energy levels of the antihydrogen through the Zeeman effect, creating a blur in the spectral signal. To find the truth, the investigators must find a way to see through this blur. To see the true signal of the broken mirror, the team must decode the influence of these messy fields. The challenge led to the work of Levi Azevedo and Claudio Lenz, Caesar, at the Federal University of Rio de Janeiro. The phenomenon is known as the AC Stark effect. When the laser pulses hit the antihydrogen, the electric field of the light distorts the energy levels of the atom. The shift is dynamic and time-dependent, changing as the atom moves through the laser beam. The distortion is particularly problematic for two-photon transitions, where high laser intensity is required to trigger the jump. The act of observation is fundamentally altering the state of the system being observed. Imagine trying to measure the temperature of a small cup of water, but the thermometer you use is boiling hot. The act of measuring the temperature changes the temperature of the water. The AC Stark effect is the hot thermometer of particle physics. If the investigators do not account for this effect with extreme precision, the subtle shift caused by a broken mirror would be swallowed by the noise of the laser. Azevedo and Caesar developed a quasi-analytical model to calculate these shifts in real time. Their work allows the Alpha team to subtract the influence of the laser and the magnetic traps, revealing the raw properties of the antihydrogen underneath. The model treats the antihydrogen as a dressed atom, a quantum system where the atom and the laser field are inextricably linked. By accounting for the way the laser pulses reshape the atom, the researchers can extract the fundamental frequencies with a clarity that was previously impossible. Researchers are essentially sharpening the scalpel, hoping that a finer cut will finally reveal the hidden bias. Furthermore, the magnetic traps also face the challenge of ionization. When the laser triggers a transition in the antihydrogen, a second photon can sometimes hit the excited atom and rip the positron away entirely. The process turns the neutral antihydrogen into a charged antiproton, which is then ejected from the trap and annihilates against the wall. The researchers must track these loss rates to reconstruct the original spectrum. Every annihilation event is a piece of data that must be captured and cataloged to ensure the final calculation is correct. The bookkeeping is a forensic nightmare, requiring the team to account for every single anti-atom that vanishes from the magnetic bottle. The alpha experiment exceeds the scope of a simple measurement. The project functions as a massive accounting job where the currency is the most volatile substance in the universe. As we look at the results from the antimatter traps, the mystery of our existence takes on a new, more profound character. The search for a flaw in the antihydrogen mirror has confirmed that nature is incredibly symmetric at the most fundamental level. The laws of physics seem to be designed with a level of fairness that is almost terrifying. And yet, the fairness is a lie. The existence of the stars, the planets, and every human observer is a physical demonstration that this symmetry was violated at the beginning of time. We are the children of a cosmic era that refuses to appear in the deep freeze of the laboratory. We are the survivors of a cosmic bias that leaves no trace in the laboratory. The alpha experiments have shown the world that if the mirror is broken, the crack is so small that the flaw hides behind the very limits of our technology. The gap between the laboratory and the cosmos is where the final answer must reside. If the known particles and the known symmetries cannot explain the matter dominance of the universe, then we must look beyond the standard model. We must ask if hidden particles exist, or undiscovered forces that operated in the first trillionth of a second, forces that have since vanished into the background of space-time. The investigation into antihydrogen has cleared away the noise, leaving a stark and uncomfortable truth. For physics, the standard model is incomplete. The universe is not what the model suggests. We are existing in a reality that should not exist, according to the laws we have written. The inquiry brings the investigation to the final question, the one that matters. If the laws of physics are this symmetric, why is there a universe at all? The search for the missing piece of the cosmic story is now moving toward the absolute edge of human knowledge. We are standing at the threshold of a new physics where the old rules of symmetry may no longer apply. The next step takes us beyond the known world, into the field of speculative theories and undiscovered particles. We are hunting for the ghost in the machine of space-time. The investigation is reaching the point where science meets the unknown. The pieces of the puzzle are all on the table, but the picture they form is still incomplete. We must find the missing mirror. The answer is out there, waiting in the darkness between the known and the unknown. Could the answer be hiding in the very particles that seem to vanish into the void? This search for a broken mirror in the heart of antihydrogen suggests that the laws of physics are far more balanced than human existence would imply. But if the symmetry is this perfect in the atoms researchers can trap, then the investigators must ask if the culprit is a particle that remains invisible to current detectors. The possibility leads the investigation away from the visible building blocks of matter and toward a ghost world of hidden twins. For decades, the standard model has relied on three types of neutrinos to explain the behavior of the weak nuclear force. These particles are nearly massless. The neutrinos travel at almost the speed of light, and the ghosts interact so rarely that billions of these particles pass through the body of a human every second without leaving a trace. But here is the thing that makes these ghosts suspicious. Every neutrino researchers have ever detected is left-handed. In the subatomic world, the handedness means the spin of the particle is always opposite to the direction of motion. Nature seems to have forgotten to build the right-handed versions of these fundamental building blocks. The absolute preference for one-handedness is one of the most glaring asymmetries in the known universe. To solve this problem of the missing twins, researchers like Laurent Canetti, Marco Drews, and Mikhail Shaposhnikov have proposed a new framework known as the Neutrino Minimal Standard Model, or new MSM. The theory suggests that the universe contains 3 additional species of neutrinos that are right-handed. Because the particles do not feel the weak nuclear force, the right-handed neutrinos are truly sterile, interacting with the observable world only through the mass of the particles and the subtle process of neutrino oscillation. The model provides a testable path to explaining 3 of the greatest mysteries in modern science at once: the masses of the active neutrinos, the nature of dark matter, and the origin of the matter-antimatter asymmetry. The investigators argue that these sterile ghosts acted as more than passive observers in the early universe. Instead, the sterile neutrinos functioned as the architects of the cosmic bias. Think of the early universe like a busy airport where every passenger is paired with an identical twin. The active neutrinos are the passengers moving through the gates and following the rules of the standard model. The sterile neutrinos are the hidden passengers moving through the maintenance tunnels. In the new MSM framework, the oscillations between these hidden particles and the visible passengers created a resonant imbalance. As the sterile neutrinos were produced in the primordial furnace, the hidden twins did not reach thermal equilibrium at the same rate as matter and antimatter. The lag, the microscopic delay in the ghost world provided the non-equilibrium condition required by Andrei Sakharov. The oscillation process allowed the sterile neutrinos to generate a large lepton asymmetry, a preference for one type of lepton over another. The bias was then handed off to the baryons through the action of spirons, those high-temperature transitions that allow baryon number to change. The ghosts were essentially stealing a tiny fraction of antimatter and hiding the stolen particles in the maintenance tunnels, leaving a slight excess of matter behind. Now, the investigation recognizes the skepticism here. The framework sounds like a convenient way to invent new particles to fix a broken theory. But the new MSCM represents an intellectually honest attempt to find the simplest possible extension of the standard model that fits all the observed data. The prosecution argues that the model is the most likely culprit because the theory does not require the invention of giant new energy scales or thousands of new particles. The evidence suggests that the asymmetry humans see today is the result of oscillations that happened when the universe was less than a nanosecond old. If these sterile ghosts exist, the particles would have masses in the giga-electron-volt range, putting the ghosts within the reach of the next generation of experiments at the Large Hadron Collider. Researchers are hunting for a signal that is nearly invisible, a phantom resonance that allowed the stars to ignite. The pieces of the ghost world may finally fit the puzzle of human existence. But wait, the case for a broken universe faces a powerful defense. While the neutrino hunters look for hidden particles, another group of investigators is checking the very foundations of space-time to see if the rules of the game are biased. The inquiry leads the search to the study of Lorentz violation and the standard model extension. Lorentz symmetry is the principle that the laws of physics do not change regardless of how a detector is moving or which direction the detector is facing. The rule is the bedrock of special relativity. The principle ensures that the speed of light is a constant and that the properties of space are the same everywhere. But if the foundation is even slightly tilted, then the preference for matter over antimatter might be a property of space. The investigation into the tilt of the universe relies on a mathematical map known as the Standard Model Extension, or SME. The framework, developed by researchers like Alan Kostelecki, catalogs every possible way that Lorentz symmetry could fail. Each potential bias is assigned a coefficient, a numerical value that describes how much nature deviates from perfect fairness. Arnaldo Vargas and the team at the University of Puerto Rico have used the latest data from the alpha experiments to test these coefficients with unprecedented precision. The investigators are looking for non-minimal operators, complex interactions that only become visible at the highest energies or the smallest scales. These operators could act like a hidden compass, giving the universe a preferred direction that matter and antimatter respond to differently. Imagine the universe as a giant pool table. Lorentz symmetry says that the table is perfectly level. No matter where the player stands or which way the player aims the cue, the balls should behave the same way. A Lorentz violation would be like having a table that is tilted by a fraction of a degree. To a casual player, the tilt is invisible, but over millions of collisions, the balls would start to cluster on one side of the table. The investigators are asking if the early universe was a tilted pool table where antimatter was slightly more likely to roll toward annihilation, while matter was nudged toward survival. The tilt would not be a property of the particles themselves, but a property of the felt on the table. The framework provides a compelling explanation for why researchers see a bias in the cosmos, but struggle to find the bias in the laboratory. If the tilt is small enough, the signal would hide behind the noise of the instruments. Arnaldo Vargas used the laser spectroscopy of antihydrogen to constrain 26 different effective coefficients within the ESSME map. Each of these bounds represents a failed attempt to find the tilt. The results of the alpha experiment showed that for transitions in the antihydrogen spectrum, the mirror is perfect to parts in a trillion. The level of agreement is a major victory for the defense. The measurement suggests that if the universe is tilted, the slope is so subtle that the tilt barely exists at all. The standard model seems to be defended by a level of symmetry that is almost impossible to break. The contradiction brings the investigation to a frustrating crossroads. The evidence from the neutrino ghosts suggests that asymmetry is hidden in the particles humans cannot see, while the evidence from Lorentz tests suggests that the foundations of space-time are stubbornly fair. So how much of the search is leading toward the truth? The prosecution has a smoking gun in the form of human existence, but the defense has a bulletproof alibi in the form of perfect symmetry measurements. The gap between theory and reality is where the mystery deepens. The pieces do not fit because researchers are looking for a massive crime using a microscope that may be tuned to the wrong frequency. To break this deadlock, the investigators are moving toward a new crime scene, the world of antideuterium. While antihydrogen is the simplest anti-atom, antideuterium represents the next step in complexity. The anti-atom consists of an antiproton and an antineutron bound together in a nucleus orbited by a single positron. Because the nucleus of antideuterium is heavier and more complex, the nucleus offers a much higher sensitivity to certain types of Lorentz violation. In regular hydrogen, the proton is relatively still, but in a deuterium nucleus, the proton and neutron are in constant, rapid motion. The internal momentum acts like a high-speed probe, allowing researchers to test the rules of physics in a regime that is inaccessible to antihydrogen. Think of the transition from antihydrogen to antideuterium like moving from a still life painting to a high-speed action film. In the painting, everything is static, and the details are easy to see. In the film, the motion reveals flaws that the still image hides. The investigators argue that the missing asymmetry might be linked to the momentum of the particles within the nucleus. By performing spectroscopy on antideuterium, researchers could improve the bounds on certain Lorentz violating coefficients by 5 to 15 orders of magnitude. The jump in sensitivity is comparable to trading a magnifying glass for an electron microscope. The advancement represents the potential for a definitive breakthrough that could finally reveal the hidden bias. The future target is the ultimate high-stakes inquiry. If the antideuterium mirror also proves perfect, then the search for a broken mirror in the building blocks of matter may have reached a dead end. But if a tiny deviation appears, the deviation would provide the first physical evidence of a bias that allowed existence to survive the primordial war. The investigators are essentially waiting for the technology to catch up to the mystery. Modern physics stands at the edge of a new field where the old rules of symmetry no longer provide all the answers. The case for human existence rests on a lucky break that seems to hide in the very motion of the subatomic world. As researchers look at the totality of the evidence, from the decaying mesons at the Large Hadron Collider to the silent traps of the Alpha experiment, a profound and uncomfortable realization begins to emerge. The investigation has confirmed that nature is symmetric to a degree that feels almost impossible. The governing principles of the universe seem to operate with a degree of impartiality that should have left behind nothing but a sea of radiation. There is no obvious reason why matter should have won the war. Every piece of the anti-world researchers have measured suggests that the twins are identical. Every test of the foundations of space-time suggests that the table is level, and yet, humanity is here. The fact constitutes the ultimate anomaly. The existence of galaxies depends on a solitary survivor out of 10 billion particles that avoided annihilation during the initial cooling of the cosmos. If the early universe had been even slightly more symmetric, the galaxies would never have formed. If the cosmos had been slightly less symmetric, the universe would be a dense, crowded mess of substance. Existence occupies a narrow window that was carved out by a microscopic error. The realization shifts the tone of the investigation from technical curiosity to existential awe. Humans are not the inevitable result of the laws of physics. Humanity is the survivor of a cosmic bias that the laws themselves seem to deny. The lucky accident of cosmic bias is the reason why every atom in the body exists. The ground beneath the feet, the air in the lungs, and the light from the sun are all remnants of a primordial struggle where the odds were 10 billion to 1 against matter. The investigation has shown that the standard model is incomplete because the theory cannot explain why the universe suffered total erasure. Humanity is the ghost in the machine of the cosmos. Humanity represents the living evidence that during the first picosecond of time, the perfect balance of the mirror cracked in a manner that eludes modern theory. The mystery of the missing antimatter is more than a problem for physicists to solve in a laboratory. The discrepancy is the story of human origin. The investigation is reaching a final verdict. The search has examined the evidence for broken baryons and the perfect mirrors in antihydrogen. Researchers have scrutinized hidden neutrino ghosts and the possibility of a tilted universe. The pieces of the puzzle reveal a reality that is far more strange and biased than history suggests. The question remains, where does the bias hide? Mankind is the child of a cosmic era, and that era is the only reason the species is here to ask the question. The verdict is almost ready. The inquiry into the mirror of matter is an investigation into the very soul of the cosmos, and the answer is closer than ever. The investigation into the origin of matter began with a single, uncomfortable fact: the universe exists. The statement sounds trivial, but to a physicist, the existence of the cosmos is the ultimate crime scene. We have spent this entire journey analyzing the evidence, and every clue points to a reality that should not be here. If the laws of physics were truly symmetric, if the mirror of the universe was perfect, then the Big Bang would have been the beginning and the end. Matter and antimatter would have emerged in equal parts, locked in a lethal embrace, and annihilated each other instantly. The result would have been a sea of pure light, expanding forever into the silence. No stars, no planets, no observers to ask why the lights never turned on. But the lights did turn on. The void is filled with galaxies, and those galaxies are filled with matter. We started this inquiry by opening the file on Paul Dirac and the 1928 prediction that doubled the known universe. Dirac realized that the mathematics of the electron demanded a twin, a shadow particle, with the same mass but opposite charge. The theoretical ghost became a physical reality with the discovery of the positron, proving that the anti-world was more than a mathematical curiosity. The anti-world was real, but the discovery created the paradox that has haunted physics for a century. If antimatter is real, where is the missing half of the universe? We looked at the cosmic ray data, the spectra of distant galaxies, and the annihilation signals from the edge of the visible universe. The answer was always the same. The universe is made of matter. The antimatter is missing. The search for the missing twin led us to the experiments of 1964 at Brookhaven National Laboratory. The discovery marked the moment the mirror first cracked. James Cronin and Val Fitch were studying neutral kaons, particles that constantly switch identities between matter and antimatter. They discovered that the kaons decayed slightly differently than their anti-partners. The phenomenon, CP violation, was the smoking gun. The discovery proved that nature does distinguish between matter and antimatter. The laws of physics are not perfectly impartial. The revelation earned a Nobel Prize and gave hope to the idea that the answer was hiding in the behavior of the quarks. For a brief moment in history, the physics community believed the case was closed. We had the motive, survival. We had the weapon, CP violation. The community felt like the pieces were finally falling into place. The universe was not symmetric, and the broken symmetry was the engine of creation. But as the champagne corks popped and the Nobel medals were handed out, a few theorists began to run the numbers. The pair took the amount of violation found in the kaons and plugged the value into the equations of the Big Bang. The researchers expected the math to spit out a universe filled with stars and galaxies. Instead, the equations spit out a ghost town. The asymmetry was there, but the effect was tiny. The effect was enough to create a single grain of sand, but not enough to build a beach. The hope of 1964 turned into the crisis of the modern era. We had found a crack in the mirror, but the crack was a hairline fracture, not the shattered glass we needed to explain our existence. We followed that hope into the modern era, tracing the map of the CKM matrix. The mathematical framework describes how quarks transform into one another, mixing and flipping identities through the weak nuclear force. The matrix allows for CP violation. The framework permits the mirror to break. We saw how the mechanism plays out in the decay of heavy particles at the Large Hadron Collider. The LHCb experiment provided the critical breakthrough, observing the first evidence of CP violation in the decay of baryons. These particles, the protons and neutrons that make up the mass of the visible world, finally showed their hand. The penguin diagrams, those rare quantum loops where quarks change flavor, revealed a distinct bias. The matter baryons behaved differently than the antimatter twins. The baryon breakthrough was significant because the finding moved the investigation from the simple world of mesons to the complex reality of the matter that actually builds us. A meson is a simple pair, a quark and an antiquark. But a baryon is a three-body problem. The system is a complex interaction of three quarks held together by the strong nuclear force. We found that in this messy, chaotic environment, the asymmetry could be amplified. The resonant regions of the decay, where the particles interact and scatter off one another, showed a bias that was clear and undeniable. We saw the signal jump to 6 sigma. We saw the smoking gun in the heavy particles. But even here, the numbers refused to balance. The baryon asymmetry we found in the lab was a triumph of experimental physics, but the result was still a failure of cosmology. The effect was real, but the magnitude was wrong. The universe requires a survival rate of 1 in 10 billion. The standard model, even with the new baryon results, gives us a survival rate of 1 in 10 quintillion. We are still missing 20 orders of magnitude. But the investigation did not stop at the high-energy frontier. We also descended into the magnetic traps of the Alpha experiment. Here, researchers took the opposite approach. Instead of smashing particles to see how the pieces die, the scientists built entire atoms of antihydrogen to see how the anti-atoms exist. Consider the sheer audacity of the experiment. To catch a ghost, you cannot touch the ghost. If an atom of antihydrogen touches the wall of the container, the atom vanishes in a burst of energy. So the researchers built a bottle made of pure magnetism. The researchers used superconducting magnets, cooled to temperatures colder than deep space, to create a field that could suspend the anti-atoms in a vacuum. For minutes at a time, the team held these alien particles in a state of suspended animation, interrogating the captives with lasers. We watched as the team used lasers to tickle the internal states of the anti-atoms, measuring the color of the light the particles absorbed. The goal was to find a crack in the CPT symmetry, the fundamental rule that says a universe of antimatter running backward in time should look identical to our own. The team measured the 1s to 2p transition, the fingerprint of the atom. The result was a triumph of precision and a tragedy for the prosecution. The antihydrogen spectrum matched the hydrogen spectrum to parts in a trillion. The mirror in the trap was flawless. Even when looking for the icy Stark effect, a subtle shift in energy levels caused by electric fields, the anti-atoms behaved exactly like regular atoms. The defense held. The anti-world is not a distorted reflection. The anti-world is a perfect copy, and the perfection is the problem. We even ventured into the ghost world of the neutrinos and the theoretical field of the standard model extension. We asked if the asymmetry might hide in the particles we cannot see, or in the very fabric of space-time. The sterile neutrinos offered a compelling mechanism, a way to generate the bias in the first moments of the universe through resonant oscillations. The neutrino minimal standard model suggests that the heavy right-handed ghosts acted as the architects of the imbalance, stealing antimatter away before the substance could destroy the matter. We also looked at the tests of Lorentz invariance, asking if the vacuum of space has a preferred direction, a tilt that nudged matter toward survival. The theories provide potential answers, but the theories remain unproven. The ghosts have not yet shown themselves in the detectors. So where does that leave the case? We have interrogated every suspect. We questioned electromagnetism, and the force was perfectly symmetric. We questioned the strong force, and the interaction refused to break the mirror. We questioned the weak force, and the force admitted to the crime, but the confession was not enough to explain the body count. We have the kaons. We have the baryons. We have the baryons, perfect mirrors in the magnetic traps. And we have the overwhelming reality of the stars. But when we try to put these pieces together, The puzzle does not form a coherent picture. The problem is not that we found no asymmetry. The problem is that we found the wrong amount. The standard model explains the CP violation we see in the laboratory. The theory accounts for the behavior of the kaons and the B mesons. The mathematics works. But when cosmologists take that known amount of violation and plug the number into the equations of the Big Bang, the math fails. The known mechanisms are efficient enough to create about one surviving particle for every 10 quintillion annihilated pairs. But the universe we see requires a survival rate of 1 in 10 billion. Let us put the gap into perspective. Imagine you are standing on the edge of the Grand Canyon. You are trying to fill the massive chasm with water. The standard model gives you a teaspoon. You pour your teaspoon of asymmetry into the void, and you look down. The bottom is not even damp. The discrepancy is more than a missing variable. The discrepancy is a catastrophe for the theory. The baryon to photon ratio is a specific number, 6 times 10 to the power of -10. The theory predicts a number with 20 zeros in front of the digit. We are missing more than a piece of the puzzle. We are missing the entire box. The discrepancy is the great gap of modern cosmology. The gap is a chasm that separates what we know from what we are. The prosecution has proved that the suspect had the means to commit the crime. Nature can break the mirror, but the prosecution has failed to prove that the suspect had the strength to pull off the heist of the millennium. The finding is a curiosity, a laboratory parlor trick that happens in rare decays. The required asymmetry is a monster, a violent cosmic scale upheaval that tore the early universe apart and left behind the wreckage of galaxies. This gap in our knowledge suggests that our understanding of the early universe is fundamentally incomplete. We are missing a massive piece of the machinery. Andrei Sakharov gave us the recipe for existence back in 1967. The man told us we needed 3 ingredients: violation of baryon number, violation of CP symmetry, and a departure from thermal equilibrium. We have found the ingredients. We found the CP violation in the quarks. We have theoretical models for the others, but the amount of the ingredients is wrong. The situation is like trying to bake a wedding cake with a single grain of sugar. The chemistry is right, but the scale is impossible. This missing piece might be the sterile neutrinos. This answer might be a new force of nature that only acted during the high-energy epoch of the first picosecond. This solution might be hidden in the dark sector, connected to the mystery of dark matter. Or the answer might be that our understanding of the initial conditions is wrong. Perhaps the universe did not start in a state of thermal equilibrium. Perhaps the game was rigged before the first whistle blew. This investigation forces a confrontation with a profound paradox. Human intuition craves symmetry. We look for balance in art, in architecture, and in the laws of nature. We build our temples with symmetrical columns. We compose our music with resolving chords. Symmetry feels right. Symmetry feels beautiful. Symmetry implies order, stability, and perfection. But this evidence tells a different story. Symmetry is death. If the universe were perfectly beautiful by our standards, the universe would be dead. A perfectly symmetric Big Bang would have ended in perfect silence. This only reason we are here to appreciate the concept of beauty is because the universe is flawed. Existence relies on a broken mirror. Life depends on a mistake. If the laws of physics were perfect, the canvas of space-time would be blank. This imperfection, the crack in the glass, the smudge on the lens that allows complexity to emerge, we are the beneficiaries of a cosmic imperfection. Every proton in your body, every neutron in the ground you walk on, is a survivor. These particles are the leftovers from a war that wiped out 99.999999% of reality. We are the fraction that remained. The realization changes the way we look at the night sky. The blackness of space is more than empty distance. The darkness is the graveyard of the annihilation. The stars are the few sparks that refuse to go out. The case of the Matter-Antimatter Asymmetry remains open. The verdict is guilty or innocent. The verdict is incomplete. The Standard Model is the most successful theory in the history of science, but the framework is an unfinished map. The theory describes the shore of the island we inhabit, but the theory says nothing about the ocean that surrounds us. The LHCb detector continues to gather data. The Alpha experiment continues to refine the lasers. The search for the electric dipole moment of the neutron continues to hunt for new sources of violation. We are still looking for the weapon. This plan for the future is already being drawn. In the coming years, the Large Hadron Collider will be upgraded to the high-luminosity LHC. The upgrade is far more than a tune-up. This change is a transformation. This upgrade will increase the number of collisions by a factor of 10, turning the trickle of data into a flood. We will be able to see processes that are currently invisible, looking for rare decays that happen once in a trillion events. We are building a machine that can see the ghosts in the machine. At the same time, deep underground in the United States, the Dune experiment will begin a new hunt for CP violation in the neutrino sector. We are building bigger eyes to see smaller things. The next generation of physicists will not be satisfied with the Great Gap. The investigators will want to bridge the impossible chasm. But this value of the investigation lies in the question, regardless of the answer. By asking why we exist, we are pushing the boundaries of what is knowable. We are building machines that cool atoms to absolute zero and machines that heat protons to the temperature of the Big Bang. We are testing the limits of our own intelligence against the complexity of the cosmos. This mystery of the missing antimatter is a reminder that we are small, but we are also persistent. The universe has kept the secret for 13.8 billion years. The cosmos has hidden the mechanism of our survival behind a veil of nearly perfect symmetry. But the crack is there. We have seen the break in the decay of the charm quarks. We have seen the evidence in the behavior of the baryons. The light is getting through. We may not have the full picture yet, but we know where to look. The mirror is broken, and because the mirror is broken, we are here to look at the reflection. The investigation continues. The file remains on the desk, and as long as questions remain, the detectives will never close the case.